Video, I'll be going through the last paper, Unified Physics, of the Specimen series. So this is for OCR Physics A, Unified paper for sample question paper under the Specimen series. So let's get started with our first question. We're given that this question is about the operation of an electrically powered shower designed by an electrical firm. Water moves at a constant speed through a pipe of cross-sectional area 7.5 times 10 to the minus 5 meters squared to a shower head shown in figure 1.1. The maximum mass of water that can flow through per second is this much. Show that the maximum speed of the water in the pipe is about 0.9 meters per second, and we are given the density of water. So I would think about this in terms of the physical quantities I'm given in terms of their units. So in order to work out the speed, if I could use the density to begin with, so if I just think about the units of density, which is kilograms per meter cube, and then I think about the amount of water that's flowing per second, so that's also the area, the cross-sectional area that it's flowing through, okay, which is 7.5 times 10 to the minus 5 meter squared. If I just look at their units, okay, so kilograms meter cube per meter cube times by meter squared, I'd end up getting kilograms per meter, which is ideal because I'm given the maximum amount of water flowing per second in kilograms per second. So if I simply, right, in terms of the units, I'm just thinking, if I divide kilograms per second by kilograms per meter, I end up getting meters per second, which is the unit of speed. Okay, so that's how I'm thinking in terms of this particular part, because there's no like set formula as that you can use. So I'm going to multiply the density, which is 1000 times by the area, the cross-sectional area through which the water is flowing, and that would give me 0.07 kilograms, 0.075 kilograms per meter. Okay, and then I just simply have to work out the speed by doing 0.075 over the mass per second, which is 0.07, and that ends up giving me 0.93 meters per second. So that's part I done. For the next part, we are given that the total cross-sectional area of the holes in the shower head is quarter that of the pipe. Calculate the maximum speed of the water as it leaves the shower head. So we know that if the cross-sectional area decreases, the speed will increase by the same amount. So all I have to do is times the speed that I calculated by 4, okay, because the smaller the cross-sectional area, the faster it would fall through the shower head. Okay, so 3.73 meters per second is my answer. For part III, calculate the magnitude of the force caused by this accelerating water on the shower head. So that's just basically thinking about force as mass times acceleration. Okay, we know that the amount of mass that's flowing per second is 0.07. Okay, so I'll just keep the units just there. Okay, per second, sorry. And then to work out the acceleration, because this mass is already in per second, I can just deal with the speed, okay, the velocity. So now I know for a fact that the water is going out at that speed through the shower holes, okay, and it was traveling into the pipe at that speed. So it is going to be the difference between the two, okay, because the pipe, obviously the water is flowing into the pipe, okay, and the water is going out through like that, okay. So the force that they will exert on the on the shower head will be obviously like that, I might have already answered part IV. Okay, well, anyway, so 0.07 times by the difference in the velocities. So I'm just going to put it down here and put it all in the calculator. So 3.73 minus 0.93 meters per second. And then you would probably appreciate how it becomes, kilograms, meters per second squared in the end, as I end up getting 0.196 as my answer. So that's basically part III done. Now, as I said, we have to, for this one, just draw the direction of the force in part III. So it is the force caused by the accelerating water on the shower head, which will be basically perpendicular to the perpendicular to the head. Okay, so that's part that's part IV done. Okay, so let's move on to the next question. Part B says, the water enters the heater at a temperature of 14 degrees Celsius. At the maximum flow rate of this much, the water leaves the shower head at that much temperature. Calculate the rate at which the energy is being transferred to the water, giving a suitable unit for your answer. And we are given the specific heat capacity of water. So we automatically know from that given information, we should make use of specific heat capacity equation, where we are talking in terms of the rate at which the energy is being transferred. So we have to think about power. Okay, so if I just write down E as P times T, I can simply calculate power by dividing both the sides by T. And one thing you'd probably notice, I'm just going to keep it like this, because I am given the mass per second. Okay, so I can just simply substitute that value into my equation and I would end up getting the answer. So the difference in temperature is going to be 16 degrees Celsius or 16 kelvins. Okay, the difference remains the same. So the rate, therefore, becomes 4,700 watts or joules per second. Okay, so that's my answer there. Let's move on to our next question, number 2. So it says a motorcyclist riding on a level track is told to stop via radio microphone in his helmet. The distance d travelled from this instant and the initial speed v are measured from a video recording. Video recording, my bad. A student is investigating how the stopping distance of a motorcyclist with high-performance brakes varies with the initial speed. Explain why the student predicts that v and d are related by this equation, where a is the magnitude of the deceleration of the motorcycle and t is the time of thinking time of the rider. Okay, so we have to think of this as along the terms of thinking distance and braking distance. So I'm just going to say that d is thinking distance and braking distance. And thinking distance depends on the thinking time. Okay, so that's simply thinking time, or well, I can just say thinking distance is just the speed times time. So it's going with the speed of v. Okay, so I can just say v times t. And we just have to think about the braking distance now. So the braking distance can be calculated using Suvat equation, because we know that it's going to come to a stop. Okay, he's going to come to a stop, and its initial velocity is just v, and this is anyway the distance that we are calculating. Acceleration is, well, actually, we can just write down acceleration as just a, because that's just what it is. It's going to slow down. Okay, so I'm just going to leave it as a for now. Okay, magnitude. All right, so t is just t is just t. Okay, so we are not really interested in that. So we can just use v squared is equal to u squared plus 2as where this is essentially 0, okay, and so u squared is minus u squared is equal to, I'm just going to say over here minus, just so that I can just cancel out the negatives, and therefore s becomes I should say v squared, my bad, because u is v, so v squared over 2a, okay, and then substitute that into my equation, and there I have my answer. Okay, so that's part A done. So for part B, it says the student decides to plot a graph of d over v on the y-axis and v on the x-axis. Explain why this is a sensible decision. So let's look back at the equation. So we know that if we are given, obviously, this form, we can say this is in the form of y equals mx plus c. However, they want us to use d over v against v. Okay, so that means that we need to modify this equation slightly and say that if we divide both the sides by v, for example, because we want that on the left-hand side, one of the v's will cancel out with v squared. Okay, so it will just give you, I'm just going to write it down as 2a v, and then v obviously cancels out with the v and gives you basically t. So that is useful because, as we know, y is equal to mx plus c, and if we compare that with the equation right here, okay, we can say that the gradient, or m, is equal to 1 over 2a. So this implies that a is 1 over 2 times m. Okay, and we can work out the y-intercept as c is simply the t, okay, the time of the thinking time. So that's what I shall say over here. You can work these out, and they are going to be constants. So that's that. Okay, now let's move on to part C. We're given that the measured values of v and d are given in the table. We need to figure out the missing value in the table, including the absolute uncertainties. Okay, so let's do that first. So d over v is just 13 over 10, which is 1.30 plus or minus. To work out the absolute uncertainty, I would have to consider the percentage uncertainties. So for d, it's 0.5 over 13. And then for v, it's just 1 over 10, times it by 100. Okay, and then I'm just going to times that by 1.3. Well, I can just leave it as I'm going to have to divide it by 100 anyway. So just going to get rid of that over there. Basically, you have that. Okay, so that ends up giving me a value of 0.18. Okay, that's fine. So which looks good. Okay, it just coincides with everything else that's given to us. Okay, then we have to use the data values to complete the table, complete the graph, and 4 have been drawn for us. Okie doke, so let's do that real quick. Okay, so from here now we're going to draw the line of best fit, and it asks us to determine the values of a and t, including the absolute uncertainty. So let's go ahead and draw a line of best fit, and I will use my trusted ruler here. And I think these points are really good because they pretty much all lie on the line as close as possible. Try to go as close as possible for that. And okay, right, so that's that. Now, to work out the values of a and t, we know from before that the gradient is equal to 1 over 2a. So let's work out the gradient of the line. I will consider taking something reasonably close to the last value, and then consider the gradient to the full extent. That will probably match right there. Okay, and that value is going to be also 0.65. I'm going to say, actually, I'm going to go for this value because it just goes better. Okay, so 0.65, and this value is right here, which is 3. Okay, so 3 minus, so the gradient is 3 minus 0.65 over the x-axis, which is for once reasonable. That is going to be 1, 2, 3, 4, 5, 6, so 36. And that's just 0. Okay, so 36, that gives me a value of 0.0652. Therefore, the value of A is equal to 1 over 2 times 0.0652, which gives me 7.66 or 7.7 meters per second squared. Okay, so that's one thing done. Let's work out the error, okay, the uncertainty, by using the gradient of the line of worst fit. I'll do this in a different color. I'll draw the steepest line and basically work from here. And I'm going to be quite cheeky about it. I'll just use the values from the table because it's the maximum of this one. Okay, so 2.94 plus 0.09, which gives me 3.03. And I'm going to use the minimum of my last date, the first data point, sorry, and that would give me a value of basically 1.3 minus 0.18, which is 1.12. Okay, so it's kind of nice. I will try to get as accurate as possible from that then. So the gradient of line of worst fit, okay, I'm doing the steepest line, and that is simply 3.03 minus 1.12 over the x-axis, which is just 35. Okay, so 35, and that's 10. Okay, so 25, and that is 0.0764. And so the value of A is going to be 1 over, as an uncertainty in A. I'm just going to say error in A for now. Okay. And that would be 1 over 2 times 0.076, and that gives me 6.545, And from here, I know that the uncertainty, if I consider the value over here, the actual value, minus the value over here, 7.7 minus 6.5 gives me 1.2. Okay, so that's my uncertainty in acceleration, and the value is 7.7. And t is, well, the y-intercept, so which we have already worked out, so 0.65. And the way you calculate, I mean, this question is not that popular. The way you calculate the uncertainty in the y-intercept is just to look at the, the steepest line, okay, and the shallowest line. So I'm just going to try and extend this in a perhaps different color so you guys can see what I am doing. So steepest line can be, I don't know whether that would actually match. I'm just going to, oops, see daisies. Let's do that again. So extend it properly. Okay, that all works right there. Okay, and then the shallowest line, which is gonna be, oh my word, okay, that will do. Okay, so right there. So that is 0.9, 0.4. Okay, so therefore the error, so that's your upper and the lower limits, okay, in the y-intercept. So the absolute uncertainty in t is equal to 0.9 minus 0.4 divided by 2, which is 0.5 over 2, which is 0.25. And if I round that to one significant figure, just like how I have over here, it becomes 0.3 seconds. So that's part C done. Wow, that was long. Okay. Now for this one, it says it was suspected that the method used to determine the distance d included a zero error, and the distance recorded by the student was therefore larger than it should have been. Discuss how this would affect the actual value of t obtained in C. Well, the actual value of t would be lower, as t is proportional to d, right? T is equal to d over v. So it's the y-intercept, okay? So the value of t will therefore be lower than what we have calculated. Okay. Question number 3. We are given that some students are asked to use the laboratory's 28mm microwave transmitter and receiver apparatus design, a demonstration to illustrate the principle of radar speed measuring device. So you've got a movable hardboard, sheet H, which is a partial reflector of microwaves, and it's placed in front of the metal sheet M, which is fixed, okay? And the student expect the detector signal to change between maximum and minimum intensity when the sheet H moves a distance of 7 millimeters towards the receiver. Okay, so 28. Anyway, so when the detected signal is passed through an audio amplifier to a loudspeaker, sound should be heard. They claim that when the sheet moves this much speed, the frequency heard should be this much. You are to evaluate whether their experiment is feasible and whether the conclusions are correct. Okay, explain why the detected signal strength should vary and discuss what factors will determine whether the difference between the maximum and the minimum can be detected. Okay, so we have to understand, let's just look at the diagram first in order to understand this question fully. So when the transmitter is transmitting some signals, it would be reflected off, okay, by H. So it's going back and forth, okay, it's going to and back, but it's also partially reflected, right? So that means that some can go towards the metal sheet, and then they would be reflected from there. Okay, so you have two scenarios. You have one where, yes, H is moving, M is fixed, okay, and as H is moving, so you have let's say the amplitude is simply A, okay, from between T transmitter and the hardboard, okay. Now, obviously, I've just drawn this for simplified purposes. It will actually be, if I just draw it properly, this is not the best diagram because it will be received by by the receiver. It would just be like this sort of thing. So it would be going to, okay, the sheet and be reflected by it, and then it would go, some of it will go through to the metal sheet and then be reflected by it. So if you say that the amplitude of the signal towards the H is A, okay, then it would be, and for all the way to M, it's like, you can say it's A, like lowercase a, okay, so that's just basically lowercase a. Then you can say that the amplitude received by the receiver, or the signal received by the receiver, will either be just A plus A, okay, as it goes from the metal the metal sheet, okay, so it's going towards the metal sheet and then coming back, okay, so that is going to be A plus A, okay, and the one that just goes to the hardboard sheet, okay, and doesn't go through to the metal piece, it would just be A minus A. Okay, so essentially the signal will vary. So I'm going to say that as some microwaves are reflected directly through H and some pass through H to M and further get reflected, they will interfere, of course. And as the waves reflect at H, whether they pass through to M or not, the sum of the displacements will vary between the maximum intensity of A plus A and minimum intensity of A minus A. And then the signal from H will increase as it moves towards R, okay, but because M is fixed, the difference of A minus A will basically increase, okay, too, as a signal from M has to travel further before being added or subtracted from A, okay? So A plus A will decrease and A minus A will increase. Hence, the detection will be more difficult if you were to consider the variation. That would definitely affect the observance of any variation between the signals, as the difference will change because H is moving, okay, but M is not. Okay, let's move on to part II. So, justify the student's predictions of 7 millimeters between maximum and minima and a sound of 200 hertz for a speed of 2.8 meters per second. Okay, so 7 millimeters between maximum and minimum. So let's understand that. So we know that the wavelength is given to us as 28 millimeters, and the distance between the maximum and minimum is basically, well, a quarter of it, right? So that's 7 millimeters. So it's 28 over 4, which is 7 millimeters, okay? And we know that the path difference is half a lambda, okay? So path difference is half a lambda. And therefore, so if we were to work out the frequency of the signal with a given speed and the wavelength, the frequency will be 2.8 over 0.028, and that will give you 100 hertz. And that is, well, that should be the frequency that would be heard at the speed of 2.8 meters per second. So that's what I'm going to say basically. Okay, so 100 hertz is the frequency heard at the speed of 2.8 meters per second. And basically when it is, so because we can see, right, that for the wavelength, so if I do 28 over 2, which is basically 14 millimeters, so every 14 millimeters the frequency would basically be affected. Okay, so that's that. So let's move on to our next question, part B. A police speed detector gun works by a different principle. Two short pulses of electromagnetic radiation at time t0 apart are fired at the front of the vehicle, which is moving directly towards the gun, and the reflected pulses are received at time t apart. A digital readout on the top of the gun displays the speed of the vehicle. In the space below, by considering how far the vehicle moves in time t0, show that the speed of the vehicle is given by that. So I feel like using Doppler effect, or, well, just the change in the wavelengths, etc. But I think I can do this just in terms of the distances. So we know that as there, I'm just going to draw this out to understand this further. So the two pulses, okay, 1 and 2, they're both basically fired and towards the vehicle, okay, car and gun, okay. And as the car is moving towards the police speed detector gun, whatever, and it basically, they're fired at t0 time apart, okay, and these are reflected back, okay, so reflected back, well, okay, back, and they are basically t seconds apart, okay, so they are received t seconds apart. Oh, okay, I've drawn the biggest diagram there. Now, we know that the distance the pulses travel is twice the distance car travels. Okay, I'll let you have a think about that, but it makes sense, doesn't it? It's back, it's 2, and back. Okay, so that's why it's twice. So in terms of the pulses, because it's electromagnetic radiation, and we have to consider therefore the speed of light. Okay, they travel at the speed of light. We can say that the distance traveled by the pulses is the speed times by the difference in the time. So they were t naught apart, and then they are received at, well, t apart. Okay, so therefore that's the time that the pulses will travel. Okay, so that's how long it will take. Okay, and that is equal to 2 times the distance traveled by the car. So that's just, say it's obviously it says it's traveling. Where does it say? Yeah, well, it says v is the vehicle speed, so it's traveling with that, and distance is therefore v times t naught. Okay, so we can just say that v is equal to c t naught minus t over 2 t naught. There you go. Okay, so that's part B done. Let's move on to question number 4. Civil engineers are designing a floating platform to be used at sea. Figure 4.1 shows a model for one section of this platform, a sealed metal tube of uniform cross-sectional area loaded with small pieces of lead floating upright in equilibrium in water. Part A says the tube has length of 300 millimeters and a diameter of 50 millimeters. The total mass of lead and tube is 0.5 kilos. Show that the length of the tube L above the surface of the water is more than 40 millimeters. So we are given the density as well. So we have to think in terms of the upthrust and the weight of the tube. So I'm going to set up an equation saying that the weight of the tube is equal to the upthrust acting on the tube due to the submerged length. Okay, so that will be now, well, let's put in some numbers. So we know that the weight of the tube can be written as mass times gravity, and upthrust is basically equal to rho vg, okay, where rho and v are basically the density and the volume of the tube, well, the density of the water and the volume displaced. Okay, so basically it's the mass displaced, right? So therefore it's rho of water, which is 1000 kilograms per meter cube, and volume, which I'm going to write down as area times by the length. And we know that the volume of the liquid displaced is equal to the volume of the object that's submerged. And I'm just going to cancel out the gravity, so I'm left with m times rho al, or 1000 al. So I'm given everything, so L is therefore 0.5 divided by 1000 times by pi, and A, well, the radius is 25 millimeters, so 0.025 squared, and that will give me a value of 0.25 meters. In other words, well, roughly, it is going to be actually I'm just going to round this. I'm not going to round this over here. I'm just going to convert it into millimeters. So 254.6 millimeters actually, which is submerged in water. Okay, so we know therefore if the total length is 300 millimeters, the length above the water is going to be 300 minus the 254.6 millimeters, and that ends up giving me, a value of 45.4 millimeters. So yes, it is more than 40 meters submerged, above the water. Okay, so that is done. So let's move on to now part B. It says, when the tube is pushed down a small amount into the water and released, it moves vertically upwards and downwards with a simple harmonic motion. The period of these oscillations, which quickly die away, is about 1 second. And the oscillation of the tube can be maintained over a range of low frequencies by using a flexible link to a simple harmonic oscillator. Okay, and so basically it's like forced oscillations. Okay, and we are given 4.2 graph shows amplitude of vertical oscillations of the tube against the frequency obtained from this experiment. And so it says, use the information from figure 4.2 to state the amplitude of the motion of the oscillator. So because it's talking about the motion of the oscillator oscillator's amplitude must meet the minimum amplitude with which the oscillations of the tube begins. Okay, so it must be 5 millimeters right here, because remember, the tube is being forced into oscillations through this oscillator. And if the oscillator is, if the amplitude of the oscillator is 5 millimeter, the tube will start its motion at the displacement of 5 millimeters. Okay, it would be displaced at 5 millimeters, but be careful. Over here we are given the amplitude of the tube motion, and over here we are asked about the amplitude of the motion of the oscillator. So the answer is 5 millimeters. And then for the next part, it says add a suitable scale to the frequency axis. So the only thing we know is that the period of the oscillations is 1 second. So we can just use F equals 1 over T, or that's just basically 1 hertz. Okay, and so I can just basically put it in the intervals of 1 hertz. Okay, so 1, 2, 3, 4, and so on. Okay, so that is my axis, x-axis. So next question says, the experiment is repeated in a much more viscous liquid such as motor oil. Draw a sketch that you would predict from this experiment. So viscous liquid will cause more damping, okay, quite heavy damping. Okay, so remember, you have light damping, you have heavy damping with liquids such as water, and then you have very heavy damping, which is in oil or glycerine, for example. If you have heavy damping, it would reduce the natural frequency and bring it down. So instead of having a peak at 2 hertz, now the peak will be slightly shifted to the left hand side, and the amplitude will also not begin at 5 millimeters. So I would just make it more flatter and shift it towards, it's a sketch, so we don't have to worry about being accurate here. So just like this, basically. So as long as the natural frequency is shifted, okay, and the amplitude does not begin at that original amplitude, you will gain the 2 marks. Okay, so let's move on to our next question now. Figure 5.1 shows a simple AC generator being tested by electrical engineers, and it consists of a magnet on the shaft of a variable speed motor being rotated inside a cavity in a soft iron core. The output from the coil wound on the iron core is connected to an oscilloscope, and the grid shows a typical output voltage which could be displayed on an oscilloscope screen. According to Faraday's law, the EMF induced is directly proportional to the rate of change of flux linkage. And in the context of this question, the maximum amplitude induced is directly proportional to the frequency of the rotation of the magnet. Use the apparatus above to plan an experiment to validate Faraday's law of EM induction. Okay. In your description, include how the data is collected and analyzed, for 6 marks. Honestly, I think this is one of the nicest questions they can ask you, because you already know the formula. Okay, I'm gonna ignore the Lenz's law and just say that EMF induced is N delta phi over delta t for Faraday. Okay, strictly talking about Faraday's law here. So they even tell you, right, that how to modify the EMF. EMF can be modified or it's proportional to the frequency. And we need to verify that. So what we need to do is basically increase the speed of the rotation of the motor and then measure the frequency from there. Okay, that's the general principle. And then plot a graph. So I'm going to start by saying to increase the speed of rotation of the motor. Then you're going to measure the time period of the generated signal each time by using the time, division on the time axis on the oscilloscope for peak to peak distance. And you're going to get your EMF versus time period in a table. And then you're going to calculate the frequency for each time period and then plot a graph of EMF versus frequency. And what you'd see is a straight line passing through the origin, as EMF is directly proportional to the rate of change in the magnetic flux linkage. Okay, and if you were to increase the frequency, right, you would also notice a increase in amplitude of the signal generated, because if the frequency increases, the maximum EMF will also increase. So that should be also considered, that should also be observed. Okay. Okay. Part B says figure 5.3 shows the poles of a powerful electromagnet producing a uniform field in the gap between them. The dimensions of each pole is 0.1 by 0.08 meters. There is no field outside the gap. A circular coil of 80 turns is placed so that it encloses the total flux of the magnetic field. And for part I, the current in the electromagnet is reduced so that the field falls linearly from 0.2 teslas to 0 in 5 seconds. Calculate the initial flux in the gap and hence the EMF generated in the coil during this time. Okay, so let's talk about the initial flux first. Initial flux is basically phi, okay, and that's just related to the initial magnetic field strength or magnetic flux density times by the cross-sectional area. So it's just simply 0.2 times by the cross-sectional area, which is 0.1 times by 0.08. Okay, so that would give me 1.6 times 10 to the minus 3 Weber. Okay, and then based on this, I can calculate the EMF, which is generated in the coil with n number of turns and in 5 seconds. Okay, so that's a really simple question, nice and easy, and you end up basically plugging all these numbers in to get an answer of 0.026 volts. Okay, next it says the coil is part of a circuit of total resistance R, so that a current is generated in the circuit while the field is collapsing. Okay, so the field is obviously decreasing, but a current is generated in the coil. Draw on the coil in figure 5.3 the direction of this induced current and state how you would apply the laws of electromagnetic induction to deduce the direction of this field, of this current. So we have to think about two laws. Number one is Lenz's law, right? And according to Lenz's law, a current is generated to oppose the magnetic field, or it would basically increase, in this case because the field is collapsing, it would increase the magnetic field. And it would therefore, so let's write that down first, okay? Okay, so now let's look at the diagram and understand how that would work. So we know that the magnetic field of the external magnet is from north to south. Okay, so we have to obviously think about the magnetic field of the wire, right? So we know that according to the right-hand grip rule, the magnetic field of the wire will want to be maintained, right? Because the magnetic field outside is collapsing. Okay, it says, right, it goes from 0.2 Teslas to 0 Teslas. So if the wire wants to encourage the magnetic field, or well, maintain the magnetic field, it would be produced in a clockwise direction. Okay, so that represents the magnetic field lines around the wire. So now if we use right-hand grip rule, okay, according to the right-hand grip rule, if you take your curled fingers in a clockwise direction now, you would notice that the current is actually acting downwards. Okay, I'm not going to attempt to draw this out because my drawing sucks, but you can try this out, right? So put your right hand around such that the curled fingers are in the clockwise direction. So you would notice that the thumb will be pointing downwards. So if the thumb is pointing downwards, I can say, so I'll just do this in a different color. So the current will be going downwards, okay? Or it will be in an anti-clockwise direction. So that's what I'm going to put down here. The current induced is in anti-clockwise direction. So I hope that makes sense. Let's move on to our next question now. Question number 6 says, an astronomer uses a spectrometer and a diffraction grating to view a hydrogen emission spectrum from a star. The light is incident normally on the grating, and we are given that the first order diffraction maxima is observed at the angles of these. Okay, and 2 of the wavelengths are given to me. Calculate the wavelength of the third line. Okie doke. So I can safely use the simple diffraction equation, right? So we know that n lambda is equal to d sine theta. Now I'm not sure whether I was looking at an older formula booklet for OCR physics, but I could be wrong, right? But I feel that this equation is not given to you, so I highly encourage you to look at it. Let's get started, right? So we know that n is 1 because it's first order maximus, and we can work out, if we can work out the value of d using the theta and one of the wavelengths, we can work out the value of the final wavelength at an angle of 19 degrees, okay, because each angle is given to us and it's increasing, so it's quite obvious which one they're referring to in this question. So anyway, so d is equal to n, I'm just going to get rid of n because that's just 1, lambda over sine theta. Lambda for the first one is 4.33 times 10 to the minus 7 over sine of 12.5 degrees, and that gives me a nice number, 2.00 times 10 to the minus 6, okay, meters. And then we can work out the new wavelength, which is lambda, with this value of d, okay, and this new value of theta, which is 19 degrees. So that's just basically really simple, and it gives you a wavelength of 6.51 times 10 to the minus 7 meters. Okie doke. Then part B says, in order to increase the accuracy of the values for the wavelength, the student decides to look for higher order diffraction maxima. State how this increases the accuracy. So if you're looking for a higher order maxima, you're basically increasing the angle. Okay, and if you're increasing the angle, the percentage uncertainty would decrease. So percentage uncertainty decreases as if the angle is larger. Okay, so that's basically that. Calculate how many orders n can be observed for the shorter wavelength given in A. Okay, so for this one, you are given, well, the maximum, right? So maximum it can go is at 90 degrees, right? So you can have as many lines as possible, that's the worst color, as many lines as possible for in between at 90 degrees. So when theta is 90, I can work out n, because n is equal to d, which is that much, sine theta, which is sine 90, over the shorter wavelength in given, which is 4.33 times 10 to the minus 7. So putting that in, I would end up getting 4.6 as n, and because it's an integer value, I would say 4. Okay, so that's part II done. Okay, part C says these three emission lines all arise from transitions to the same final energy level. The part of the energy level diagram of the hydrogen relevant to these transitions is shown. Draw lines between the energy levels to indicate the transitions which cause the three emission lines and label them with their wavelengths. Okay, so we know that the energy gap, which is also proportional to the energy of the photons, or in this case, the energy of the wavelength corresponding to the wavelength, is inversely proportional to the wavelength. Okay, it's like hc over lambda, right? So therefore, the biggest gap will be corresponding to the smallest wavelength. So I'm gonna go with that. The first one will be for 4.33 times 10 to the minus 7 meters, followed by the second one, which will be the middle wavelength, which is 4.84 times 10 to the minus 7, followed by the last one with the highest wavelength, and therefore the shortest energy gap will be 6.5 times 10 to the minus 7 meters, 6.51. Okay, so that's my part CI done. For II, it says there are other possible transitions between the energy levels shown in figure 6.2. The least energetic of these produces photons of this much energy. Calculate the wavelength of these photons and state in which region the of the EM spectrum this wavelength is found. So we know, as I said earlier, E is equal to hc over lambda, which is the energy of the photons, which is equal to the energy of the in between the gaps. Okay, so basically, if I want to work out the lambda, I can just rearrange as hc over delta E. And because I'm given pretty much everything, I'm given, the energy gap as well, I can just put everything into the calculator, okay, and end up getting a value. Let's see, that's that, and 10 to the minus 20. And I end up getting 4.14 times 10 to the minus 6 meters. And the region is very close to visible, but visible is 10 to the minus 7 rather than 10 to the minus 6. So it's going to be infrared. Worth remembering the wavelengths. Okay, infrared region. So worth remembering the wavelengths, or the order, rough order, not even rough order. What I mean is obviously a range. Okay, that would be good. So let's move on to our next question now. Number 7. Describe the processes of fission and fusion of nuclei, stating one similarity and one difference between the two processes. Describe the conditions required for each process to occur in a sustained manner. So, so we know that fission is when a heavy, unstable nucleus absorbs a neutron and splits up into smaller, more stable nuclei and neutrons, giving off large amount of energy. Whereas fusion is when two unstable nuclei join to form a bigger nucleus. And this one requires energy. It's an endothermic process, and you need very high temperature and pressure to initiate it, okay, unlike fission, where you just basically need a neutron and a heavy nucleus. So you need high temperature and pressure, obviously, to overcome the strong electrostatic forces of repulsion between the nuclei. And this process releases smaller amount of energy compared to fission, They both cause an increase in binding energy, so that's one of the similarities. And for fission to sustain, you basically need, fission to sustain in a controlled manner, you need control rods, which are basically used in nuclear fission reactors to absorb excess of neutrons. So yeah, that's basically what I'm going to say here. Part B, it says uranium-235 is used in many fission reactors as fuel, and fusion reactors are still at an experimental stage. Suggest one major disadvantage of having fission reactors. You can put lots of things. You can say one of the major disadvantage is radioactive waste, or danger to humans who are working there. So anything. So I'm going to just say radioactive waste as the major disadvantage. So part II says the fission of a uranium-235 nucleus releases about 200 mega electron volts of energy, whereas the fusion of 4 hydrogen-1 nuclei releases only about 28 mega electron volts of energy. At first sight, it would appear that the fusion would produce less energy than fission. However, the energy released in fission of 1 kilo of uranium is about 8 times less than the energy released in fusion of 1 kilogram of hydrogen-1. Explain this by considering the initial number of particles in 1 kilo of each. Okay, this is a nice question because it's just based on calculations. So we can work out the, so I'm just going to draw this out like a little table. So uranium-235 versus hydrogen, 4 hydrogen 1 nuclei. Okay, so we can work out the number of particles in 1 kilo. Okay, number of particles in 1 kilo of each. Okay, now we know that the 235 is in grams, and we know how many how many particles are in 1 mole of uranium-235, which is the Avogadro's constant. So if you have, so I can just work this out like 1 kilo. I'll just convert this in, I'm just going to keep it as 1 kilo and times it by 6.02 times 10 to the 23 particles per mole over 0.235 kilograms per mole. So that's just basically going to give me the particles, the number of nuclei. So that's 2.56 times 10 to the 24 nuclei in 1 kilogram of uranium-235. Likewise, I'm going to do it for hydrogen. So 1 times 6.02 times 10 to the 23 divided by 0.001. And I would end up timesing this by 4, okay, to get the amount. In fact, I'll just write that down over here, which is 6.02 times 10 to the 26. And now I can work out the amount of energy released in total. So energy released is going to be 2.56 times 10 to the 24 times by 200 MeV, which gives me 5.12 times 10 to the 26 MeV, okay, because these many particles are in 1 kilo, and we are given that this is the amount of energy, this is the amount of energy per fission. Okay, so, and we are then given that 4 hydrogen 1 nuclei will release 28 MeV. Okay, so I can just basically, energy released over here will be therefore 6.02 times 10 to the 26 times by obviously 4 times as much. So 4 times 28 MeV. Okay, so that will be 4.21 times 10 to the 27 MeV. And now if I just look from, check out this into that, I would end up getting roughly about 8.2. So this basically shows, so if I just times it by 8.2 something something, I would end up getting my answer. So that's basically how you do this part. So that's the end of the question paper. I hope you found this useful, and good luck for paper 3. I hopefully will be releasing the last paper of practice paper series. Hopefully, right? I can't guarantee if I would get a chance, but I will do my best to release it. But otherwise, anyway, good luck for your paper 3.